entanglement beyond qubits or high-dimensional entanglement for quantum communication. So first of all, maybe a short word on information. Well, we all know, I mean, in the end, all information that is finite can be encoded in bit strings, and just as well, quantum information can be encoded in qubit state vectors. And the main difference, of course, is the possibility to create superpositions, the basis for all entanglement computing, and the necessary requirement for useful quantum communication. So, I mean, that's all done, and we're mastering it slowly, piece by piece. The main question being, why even consider higher dimensional alphabets? I mean, we can, classically, we could just as well. We could have a quart with 4 states, but indeed, it's just equivalent to 2 bits. And the same is kind of true, right? Any composition of qubits can be seen as a quart. And any information processing I can do with quarts, I can also do with qubits, or at least in the ideal case. In the ideal case of pure states and perfect control. And in the classical case, there is no real need to consider DITs, mostly for the reason that you can, anyway, all the bits you define are redundant, they are thus very noise resistant, they are easy to copy and amplify, and therefore there's no need to even go into the details of more physical degrees of freedom that you encode into. But the situation becomes a bit different in the quantum case, because now, in order to have coherent superpositions, we can't just encode in very emergent, large-scale, macroscopic degrees. We really want to get to control fundamental degrees of freedom, single excitations of certain orbitals of atoms, as we've just heard, or the polarization of a single photon, the path of a single photon, and so on and so forth. And this limited by our ability to control and isolate. And once entanglement and quantum information is gone, we can't just copy it arbitrarily. And part of this entire conference is devoted to the fact that this is difficult, and we can't just build trivial repeaters that will just refresh our quantum entanglement with ease. Yeah, so just a quick primer on entanglement for pure states. So any quantum state I can write in the also many times mentioned Schmidt decomposition, and the number of non-zero terms in the Schmidt decomposition is the Schmidt rank, and this is kind of the dimension of entanglement. It's the number of degrees of freedom I essentially need to faithfully represent all the correlations in the state. That's why it's also often called the dimensionality of entanglement. Now, of course, we all know pure states are a fiction, and especially in quantum communication, we'll have to basically accept the fact that we'll suffer significant noise and decoherence no matter what we do, especially as we increase distances, and maybe also affordability of devices. Of course, the entanglement dimensionality is just as easily defined for mixed states. If you have an ensemble, any density matrix can be decomposed into a convex sum of pure states. And formally, you can define the dimensionality of entanglement, or the Schmidt number of a density matrix, just by the infimum over all decompositions of the maximum Schmidt rank within such a decomposition. It looks a bit bulky, and indeed it's not the easiest to compute. I mean, we all know it's even NP hard to decide to whether a state is entangled or not in the first place. So, of course, computing the Schmidt number exactly for any given density matrix is out of the question, but we can bound it very well. But okay, I've hinted at it, but why would we consider even these higher dimensional systems and degrees of freedom? And a very common narrative in this respect is an advantage with respect to noise. So let's do a very simple thought experiment where we think about an ideal source creating a maximally entangled state in d dimensions, a phi plus state I call it, and at the same time other influences like dark counts, environmental photons, and others create coincidence clicks in our two detectors that are not caused actually by the maximally entangled state of the source, but by a confluence of random photons in the background or random dark counts in the background, and this is what we call an accidental. And now if we basically write the resulting density matrix that we would reconstruct after a full state tomography, or essentially any measurement would be compatible with that density matrix, with a probability of accidentals being PA, the density matrix would essentially be, well, 1 minus PA to phi plus. Like, there's no probability of an accidental, we just get the perfect state, plus with the accidentals being essentially uniformly distributed. I mean, that is the case if our degrees of freedom or our measurements or accidentals are equally likely for each configuration of basis elements, which is the case in most places. And now one of the curious facts that is often used to argue noise resistance is the fact that the critical probability for a coincidence to be an accidental, for the state to not exhibit any more entanglement, it scales as d over d plus 1, i.e. once you go to very high dimensions, you can tolerate easily 99% accidentals, something that would completely obliterate any qubit entangled state. We all know that for a qubit, well, we can see here, 2/3 would be the limit. So like once you have more than 2/3 of noise, your qubit entangled state is in fact no longer entangled and it's useless. And that's a compelling story, but also that's what it is. It's a story. The fact is that, of course, if it were so simple, then we would just need to go to higher and higher dimensions to defeat all kinds of noise. However, of course, the probability of an accidental is not completely independent of the dimension I use, not independent of the degree of freedom I use. And also the information processing and the post-processing and the measurements and everything else gets harder as I increase dimension. So there are a couple of really big challenges in really utilizing these high-dimensional systems. So first of all, physical availability. Where do we even find high-dimensional entanglement in the first place? Because if it were so much more expensive to create than the qubit counterparts, then it really wouldn't make sense to even pursue that route. Luckily here, one can say that it is routinely generated in almost all down conversion experiments, which are anyway the working force of most photonic quantum communication. Then the next question is like, how do we confirm the presence of entanglement? What kind of measurements can we even do? Like for a polarization qubit, it's very easy to do all the possible quantum measurements, sigma x, sigma y, sigma z. We basically need a half-wave plate and a polarizing beam splitter, and we can do all the measurements we need. Once we encode in other degrees of freedom, like orbital angular momentum, spatial modes in general, or the frequency, or time bins, it is no longer trivial to do all possible measurements. And the second thing, what I mentioned before, is, well, when does the noise actually scale in such a way that we find a favorable advantage from utilizing the full spectrum? And finally, just because we can distribute entanglement in super noisy scenarios, does that even mean that we can do any meaningful quantum communication? So yeah, let me try and find a few words regarding all of these points. So first of all, what I've said before, luckily, down conversion rests upon the conservation of physical degrees of freedom that are continuous anyway, and any discretization thereof then leads to usually very high dimensional entanglement. So for instance, the conservation of momentum implies very strong spatial entanglement. This is essentially what is used for generating entanglement across different paths, different spatial modes on an optical chip, between orbital angular momentum modes in free space communication. And similarly, energy conservation essentially implies very strong entanglement across frequency modes and also across temporal modes in time-bin implementations. Here, just as an example, for instance, the quantum state of a single photon pair in orbital angular momentum basis will typically look a little bit like this, where I have some Schmidt coefficients lambda I, and the signal and idler photon will have to have exactly the opposite momentum due to momentum conservation, and the pump beam having OEM of 0. And yeah, so at least we can routinely generate high-dimensional entanglement, but then how do we confirm presence and what kind of measurements can we do? So one of the other challenges is that really reconstructing the entire quantum state is a bit annoying, simply because of the dimensionality involved, the number of measurements that we would need. And so, for instance, if you do a full state tomography, we need d+1 squared global combinations. So if we're really going to a 1,000-dimensional system, this is already a million different measurement settings. This is, yeah, cumbersome. But luckily, many states admit a much more efficient certification with fewer measurements. So if we just want to know the fidelity to our target state, because full state tomography is like basically, I don't know, searching a needle in a haystack randomly, because we already know what kind of states we aim to create, and doing all of those measurements that we wouldn't even expect to yield any correlational result is, of course, over the top. By basically just doing the measurements that would certify our target state fidelity, we can be a lot more efficient. And even 2 measurements for all dimensional systems can be enough if the state is pure enough. So here I just quickly want to mention a technique using mutually unbiased bases, a very typical technique in higher dimensional systems. So 2 bases are mutually unbiased if their respective state vectors of the 2 different bases all have overlap 1/d. And those can be used to quantify and certify entanglement even with just 2 bases. In fact, there is this one theorem we once proved that every state is in fact uniquely determined by measurements in Schmidt bases and 1 tilted basis. So we only need 2 measurements to uniquely determine the correct fidelity for each pure state, and we can use those same measurements to bound the fidelity also for mixed states. So this, after we came up with this theorem, this was one of the first things we did in our own lab. It was run by Miho Malik at the time, where we essentially entangled photons in their orbital angular momentum degree of freedom and determined the computational basis correlations that you see here, and then constructed the kind of mutually unbiased, or in that case tilted basis, and with these 2 measurements we were able to confirm the presence of high-dimensional entanglement in orbital angular momentum with just 2 global measurement settings. And now we basically continue that story to investigate the question of, well, when is there actually a noise advantage? So here we did 2 experiments, one in the group of Rupert Ursin, using time-bin entanglement, and another one in my group back then, using again orbital angular momentum entanglement, where we actually artificially, first we thought it's enough to turn on the light in the lab, but it was still not enough to get rid of all the entanglement. Then we basically installed light bulbs next to the APDs. Even that was not enough to kill our detectors, also because we realized that they have a strong time dependence because of the frequency of the AC. So in the end, we had to be a bit clever about light sources, but we infused a lot of extra accidentals and essentially found that there are two pathways of increasing noise resistance using high-dimensional entanglement in practical entanglement distribution. Well, one of them is to the fact that we can keep adding more and more measurements and more bases in higher dimensions. And the other is, since it's a continuous degree of freedom, like for instance in time bin, we can keep fine-graining correlations or measurements, i.e. choose smaller and smaller time bins until we reach jitter noise. And by doing so, we're essentially diluting all of the accidentals and therefore are able to confirm presence of entanglement, even in scenarios where the total accidentals exceed 90%. Yeah, so these are the two plots of these two implementations. But you see another very significant thing. One of them would be that as you increase the dimension, you basically already start increasing the noise by itself, because by decreasing the time bin size, what you're doing is you're also seeing more jitter noise. So by increasing dimension, you're increasing the noise and increasing the noise robustness, and it's kind of a competition that you still want to be on the winning side, but by doing it too much, you lose again. So it's really a technological challenge. So the next main question would be, okay, so I can distribute entanglement that is super noisy, but does that get me anywhere? Because in the end, for QKD, for instance, the error correction just kills me. Yes, I have like some tiny bit of entanglement in a very high dimensional alphabet and tons of noise, then the error correction essentially kills all key rate. So we came up with an idea of basically using flexible subspace QKD in this kind of PRA applied paper, where you can show that you basically, in a d-dimensional system, you use k-dimensional subspaces. And for low noise, it's best to use the full space and no subspace. And for high noise, it's best to simultaneously code in low-dimensional subspaces. And there have also been first experimental implementations. And here, yeah, here's again, you see there are actually 16 detectors altogether, 8 for each side. But when doing this, this is exactly what you see. You can, and this is my final slide, you can see that as I increase the dimension, as I add more and more paths, I can really get the key rate in bits per second, the post-processed key rate after error correction, private simplification, and everything else. I can increase it with low noise. And again, by turning on lamps, we injected extra coincidences. And as we add more and more extra coincidences, or I should say accidentals, you can see that at some point, the higher dimensional case loses out and these key rates drop to 0. And actually low dimensional subspaces of high dimensional systems are the best for this kind of QKD. Yeah, I guess in the interest of timeliness, I should stop here. There is also a review paper we've written on high dimensional and multi-qubit entanglement with Nico Giuseppe from my group and Mehul, who is now in Edinburgh.
Okay, thank you. Let's thank Markus for the talk. And now I'll ask the general questions. What will be the first use case for entanglement-assisted communication networks?
Well, I guess anything that has extremely high requirements on privacy and data security. I mean, I kind of have the feeling that most classical communication is anyway secure enough for most purposes, and there's such a volume in the internet of communication, most of which is sufficiently to be secure enough. So I don't know what this would be. Maybe, as the previous speaker said, maybe governments, banks, or, well, I don't know. I guess this is for the communications people to figure out.
Okay, and on the path of realizing this use case, what is the current main challenge in your field?
So, well, I guess distance and key rate, those need to be increased. Like, we need more bits per second, and we need to be able to do this over longer distances. And I do not know which is the best technological way forward. My guess, my gut feeling would be probably satellites and high-dimensional systems, but I guess this is still an open scientific question.